Okay. I was gonna read another page of kids. I actually did this earlier with this, and I was gonna pick up where I left off and finish it at the pictures. But the camera that I was trying to transfer the video onto the computer to upload it onto the YouTube, and that didn't work because the cord is not the right thing, and I tried to go buy another one, but I couldn't remember what the name of the cord was, and so I'm just gonna not. I just want to get to this part down here, down the line. So I'll left off where I put this last time, and then tomorrow I'll find the cord, and then I'll do something about that probably. I don't really know. Also, I don't know where my vape is. That I'll see if that becomes a problem. I don't know if it will. Anyways, I want you to be able to see the. Whatever, this is fine. Meantime, okay, and this is the page. Look at how it's got this. It's got like wormholes in it. So, in the northeastern United States, I'm gonna calm down a bit. The best place to study earthquakes is the Lamont Doherty Geophysical Observatory, a group of unprepossessing buildings hidden in the woods of southern New York State, just west of the Hudson River. Lamont Doherty is where Christopher Sholes, a Columbia University professor specializing in the form and structure of the solid earth, first started thinking about fractals. And fractals is cut in half into fractal. Look, fract. You see it? Fractals. While mathematicians and I won't keep doing that, but while mathematicians and theoretical physicists disregarded Mandelbrot's work, Sholes was precisely the kind of pragmatic working scientist most ready to pick up the tools of fractal geometry. He had stumbled across Benoit Mandelbrot's name in the 1960s. That's been a problem for me lately. I just cannot stop. Mandelbrot's name in the 1960s. When Mandelbrot was working in economics and Sholes was an MIT graduate student, spending a great deal of time on a stubborn question about earthquakes. It has been well known for 20 years that the distribution of large and small earthquakes followed a particular mathematical pattern. Precisely the same scaling pattern that seemed to govern the distribution of personal incomes in a free market economy. This distribution was observed everywhere on Earth, wherever earthquakes were counted and measured. Considering how irregular and unpredictable earthquakes were otherwise, it was worthwhile to ask what sort of physical processes might explain this regularity, or so it seemed to Sholes. Most seismologists had been content to note the fact and move on. Sholes remembered Mandelbrot's name, and in 1978 he bought a profusely illustrated, bizarrely erudite, equation-studded book called Fractals, Form, Chance, and Dimension. It was as if Mandelbrot had collected in one rambling volume everything he knew or suspected about the universe. Within a few years, this book and its expanded and refined replacement, The Fractal Geometry of Nature, had sold more copies than any other book of high mathematics. Its style was abstruse and exacerbating, by turns witty, literary, and opaque. Mandelbrot himself called it a manifesto and a casebook. Like a few counterparts in a handful of other fields, particularly scientists who worked on the material parts of nature, Sholes spent several years trying to figure out what to do with this book. It was far from obvious. Fractals was, as Sholes put it, not a how-to book, but a gee-whiz book. Sholes, however, happened to care deeply about surfaces, and surfaces were everywhere in this book. He found that he could not stop thinking about the promise of Mandelbrot's ideas. He began to work out a way of using fractals to describe, classify, and measure the pieces of his scientific world. He soon realized that he was not alone, although it was several more years before fractal conferences and seminars began multiplying. The unifying ideas of fractal geometry brought together scientists who thought their own observations were idiosyncratic and who had no systematic way of understanding them. The insights of fractal geometry helped scientists. Okay, don't be alarmed if I just start puking suddenly for some reason, because that just keeps happening. I start dry heaving all the time. It's really when my attention gets too The insights of fractal geometry help scientists who study the way things meld together, the way they branch apart, or the way they shatter. It is a method of looking at materials, the microscopically jagged surfaces of metals, the tiny holes and channels of porous or oil-bearing rock, the fragmented landscapes of an earthquake zone. As Scholl saw it, it was the business of geophysicists to describe the surface of the Earth, the surface whose intersection with the flat oceans make coastlines. Within the top of the solid Earth are surfaces of another kind, surfaces of cracks, faults, and fractures to dominate the structure of the Earth's surface, that they become the key to any good description. More important on balance than the material they run through. The fractures crisscross the Earth's surface in 3 dimensions, creating what Scholl whimsically called the schizosphere. They control the flow and fluid through the ground, the flow of the water, the flow of oil, the flow of natural gas. They control the behavior of earthquakes. Understanding surfaces was paramount, yet Scholl believed that his profession was in a quandary. I don't know what a quandary is. In truth, no framework existed. Geophysicists looked at surfaces the way anyone would, as shapes. A surface might be flat, or it might have a particular shape. You could look at the outline of a Volkswagen Beetle, for example, and draw that surface as a curve. The curve would be measurable in familiar Euclidean ways. You could fit an equation to it. But in Scholl's description, you would only be looking at the surface through a narrow spectral band. It would be like looking at the universe through a red filter. You see what is happening at that particular wavelength of light, but you miss everything happening at the wavelengths of other colors, not to mention the vast range of activity at parts of the spectrum corresponding to infrared radiation or radio waves. The spectrum, in this analogy, corresponds to scale. To think of a surface of a Volkswagen in terms of its Euclidean shape is to see it only on the scale of an observer 10 meters or 100 meters away. What about an observer 1 kilometer away or 100 kilometers? What about an observer 1 millimeter away or 1 micron? Imagine tracing the surface of the Earth as it would look from a distance of 100 kilometers out in space. The line goes up and down over trees and hillocks, branching, and in a parking lot somewhere, a Volkswagen. It goes over a Volkswagen. On that scale, the surface is just a bump among many other bumps, a bit of randomness. Or imagine looking at the Volkswagen from closer and closer, zooming in with a magnifying glass and microscope. At first, the surface seems to get smoother as the roundness of the bumpers and hood passes out of view. But then, the microscopic surface of the steel turns out to be bumpy itself in an apparently random way. It seems chaotic. Scholl found that fractal geometry provided a powerful way of describing the particular bumpiness of the Earth's surface, and metallurgists found the same for the surface of different surfaces of different kinds of steel. The fractal dimension of a metal surface, for example, often provides information that corresponds to the metal's strength, and the fractal dimension of the Earth's surface provides clues to its important qualities as well. Scholl thought about a classical geological formation, a talus slope on a mountainside. From a distance, it is a Euclidean shape, dimension 2. As a geologist approaches, though, he finds himself walking not so much on it as in it. The talus has resolved itself into boulders the size of cars. Its effective dimension has become about 2.7 because the rock surfaces hook over and wrap around and nearly fill three-dimensional space like the surface of a sponge. Fractal descriptions found immediate application in a series of problems connected to the properties of surfaces in contact with one another. The contact between tire treads and concrete is such a problem. So is contact in machine joints or electrical contact. Contacts between surfaces have properties quite independent of the materials involved. They are properties that turn out to depend on the fractal quality of the bumps upon bumps upon bumps. One simple but powerful consequence of the fractal geometry of surfaces is that surfaces in contact do not touch everywhere. The bumpiness at all scales prevents that. Even in rock, under enormous pressure at some sufficiently small scale, it becomes clear that gaps remain, allowing fluid to flow. To Scholl, it is the Humpty Dumpty effect. It is why two pieces of broken teacup can never be rejoined, even though they appear to fit together at some gross scale. At a smaller scale, irregular bumps are failing to coincide. Scholl became known in his field as one of the few people taking up fractal techniques. He knew that some of his colleagues viewed the small group as freaks. He used the word fractal in the title of a paper. He felt that he was regarded either as being admirably current or not so admirably on a bandwagon. Even the writers of papers forced difficult decisions between writing for a small audience of fractal aficionados or writing for a broader geophysical audience that would need explanations of the basic concepts. Still, Scholz considered the tools of fractal geometry indispensable. I'm at 10 minutes. My phone will probably run out of storage. But what I'm going to say next, I really wanted to get to the end of this thing. This is basically like my 15-minute breaks. I have 30-minute breaks, but like by the time I was like going to the thing, to the stairwell, it's like sort of the same thing. Look at this page is almost like, it's really bent. I wonder how that happened. Anyways, I got to get to the next page, okay? It's fine. It's a single model that allows us to cope with the range of changing dimensions of the Earth, he said. It gives you mathematical and geometrical tools to help make predictions. Once you get over the hump and you understand the paradigm, you can actually start measuring things and thinking about things in a new way. You see them differently. You have a new vision. It's not the same as the old vision at all. It's much broader. Okay, actually, I'm going to wait for the next part because then I won't be so like it's the end of the day right now. I could do better for the next one. So I'll get one of my Post-it. See, I put red because that's the color of my raspberry vape. I put that on the other. It was kind of a worse angle. These things I got today, they're Post-it. They're called Post-it flags. That's what I put on the last video, but I can't do anything about that one because it's like, how far did I put this? I could just use painter tape to do this, but whoops. That looks fine. See, and now I'm not really, it started off random, and then it may get random again at some other point, but then it'll just, I don't know, the first one I don't have, because I really just want it to be on the other computer, because then I pick up that recording thing and I just add other things, like what's outside my window. That's an interesting thing, or like, well, to me, like for me to look back, so I just think that I don't know. I don't know. Just need to output something. So, yeah.